Hi, so I'll be talking today about TASE, a symbolic execution tool that we've developed that uses transactional memory to reduce the latency of symbolic execution. I'm Adam Humphreys, and this is joint work with Kartik Keating Subramanian, advised by Mike Ryder. So briefly and hopefully as a review, I'll talk about what symbolic execution is. So symbolic execution is a technique for analyzing programs. So for example, suppose you have the test me toy program pictured above, and you want to know whether or not error can be printed given some inputs to test me. So we can analyze test me with symbolic execution by marking the inputs to test me, X and Y, as symbolic variables, and tracking every possible branch and execution that could possibly result depending on those input symbolic variables. So in other words, we don't actually assign concrete actual numbers to X and Y. So for example, in the figure on the right, you can see a representation of the control flow we get when symbolically executing test me. The first if statement in test me triggers if 2y is equal to x. So we perform a kind of a fork operation to represent the two states of execution that represent the true and the false branches. And we add constraints to each of those two branches to represent the condition tested in the if statement, that either 2y is equal to x or 2y is not equal to x. And similarly, in the true branch, we create two states based on the if test for x is greater than y plus 10, either succeeding or failing, along with the corresponding constraints for the outcome of the if test. And so you can see that by using a SAT solver to solve for possible solutions to the conjunction x is equal to 2y and x is greater than y plus 10 on the bottom right hand corner there, we can get a completely concrete input to the program that would drive execution to the error statement. Okay, so our symbolic execution tool TASE is designed to efficiently perform concrete operations while performing symbolic execution. And so while symbolic execution research and design has historically often focused on challenges such as path explosion, or in other words, navigating a large space of program executions, and the cost of constraint solving, this problem of efficiently mixing fast concrete computation into symbolic execution has gained more importance recently. It's been highlighted in recent research papers, and it's also been shown to be important for online latency-sensitive uses of symbolic execution. So later in the evaluation section of this talk, we'll talk about one such application called behavioral verification and show how TASE improves its performance. So what does TASE actually do to solve this problem I mentioned on the previous slides of supporting fast concrete operations mixed in with small amounts of symbolic computation? So we use specialized hardware, Intel's TSX instructions, to speculatively execute code natively within a transaction, and then later we abort the transaction if we determine that it operated on symbolic data. So specifically, we execute the program under analysis within transactions, and we use a poisoning scheme to mark memory that contains symbolic data. So when we're executing natively in TASE, we store memory values read or written to in SIMD registers, and we check them in batches before a transaction is committed to determine if a poisoned symbolic value was accessed. And if symbolic data was accessed, we undo the transaction with the transactional hardware and fall back to a slow but safe interpreter to handle the symbolic computation. So I'm going to show a cartoon that sort of demonstrates the idea behind TASE's instrumentation. So TASE's instrumentation works at the level of machine code. So I've included a snippet of code representing 3 machine instructions that grab a value incremented by 1 and store the result. And so the idea behind TASE's instrumentation is that we copy the operands used by each instruction without immediately performing checks on them. So later at the end of a basic block, we can en masse check the operands and determine if any of them were actually symbolic. And if so, we roll back the transaction and re-execute the basic block in an interpreter capable of handling the symbolic data. So I'll talk more about how we specifically detect symbolic data and roll back transactions, but later on. But first, let's talk a little bit about the hardware that lets us implement this speculative execution scheme. Okay, so briefly as an aside, I'll say a little bit about these TSX instructions that are actually used to implement transactions. So they're x86 instructions that allow a series of instructions to be executed atomically. So either all of the code in the block of code in the transaction executes or none of it does. So specifically, these TSX instructions are the X begin, X end, and X abort machine instructions. And they were originally created to help the performance of programs with concurrency. And so I have a small example of a transaction on the right here. The three instructions in the transaction, the same instructions in the previous slide, will either all occur or not occur at all. So to recap, these TSX instructions are machine instructions, and in TASE, if the transaction doesn't successfully reach the X-end instruction and complete, we fall back to an interpreter. Okay, so I'll talk now a little bit more about how TASE actually detects the use of symbolic data during a transaction. So the strategy is that we mark individual bytes containing symbolic data with a reserved poison value when data is initially marked as symbolic. And then later, when TASE is attempting to execute code natively within a transaction, the contents of memory written to or read from are stashed in wide SIMD registers. And at the end of the transaction, or sooner if we fill up those SIMD registers earlier, we check those registers en masse to detect if the reserved poison value is actually encountered. And if so, we abort the transaction. And so the idea is that this delayed poison checking can be implemented with relatively few machine instructions as instrumentation compared to, say, compiling in checks before each machine instruction executes that consults a bitmap somewhere. And to make the comparisons more efficient, at the end of the transaction, we borrow a technique used by taint trackers to batch up the poison checks with SIMD registers. We do have to worry about false positives in this scheme. There are more details about that in the paper. But to summarize briefly, the interpreter also maintains a bitmap to address cases where a concrete byte might happen to be the poison value. So I'll also talk a little about how we structure transactions in TASE. Or in other words, just simply where do we place those special TSX instructions that begin and commit the transaction. So unfortunately, it's not particularly feasible to place just every single basic block in a TSX transaction. There's an overhead cost associated for setting up and committing transactions. And so running code with that strategy has been estimated to give an 8 to 20 time overhead relative to normal execution. So in other words, we don't want our transactions to be too small. On the other hand, the maximum size a transaction can have is limited by cache size and associativity. So the transactions can't be too big. So we have a kind of a problem with getting just the right number of instructions placed inside each transaction. And our solution, at least in TASE, is ultimately to observe that although we assume TASE has access to the source code of the programs it's analyzing, and we might know the control flow graph, for example, we can't completely know statically in every case exactly in what order the basic blocks will be executed at runtime. So we adopt a scheme where we dynamically count the number of basic blocks executed at runtime. And the idea is that there's some fixed number X of these basic blocks per transaction, and we experimentally determine X. So I've got a picture on the right here that shows the structure of TASE and hopefully also kind of wraps everything together that we've talked about so far. There's a lot of detail here, and it's broken down into pieces in the paper. But for now, the important thing to take in is that we require source code for the program we're analyzing, and we inject instrumentation with a custom LVM compiler pass at the machine code level. So we're modeling the address space and also the general purpose registers. And the picture on the right shows that all the components go into a single address space, both the native execution and interpreter pieces. The interpreter is CLI-based and it interprets through emulated x86 contexts until no symbolic data exists in the emulated registers. And when the emulated registers are entirely concrete and the interpreter reaches the beginning of a basic block, it restores a context and native execution can resume. To measure TASE's performance, we included some micro benchmarks in the paper and an evaluation of TASE on an online latency-sensitive security application of symbolic execution called behavioral verification. And so in the interest of time, I'm going to focus on the behavioral verification evaluation part for this talk. So the idea of behavioral verification is that you can apply symbolic execution to build a tool that acts much like an IPS, like an intrusion protection system. And this tool checks to see if an incoming message M coming in could have been produced by a known program P, for example, a client implementation of some protocol. And the tool symbolically executes the known program P by making its unknown, perhaps client-side inputs symbolic, and trying to drive execution to a line of code in P that would be, for example, a send syscall that transmits the observed message. So interestingly, the most recent work on behavioral verification, which applied the technique to TLS client verification, found that over 97% of the instructions executed during the verification actually operated completely on concrete data. And that's part of why, as we'll see shortly, TASE improves the performance of behavioral verification for TLS. Okay, so I'm going to talk about that a little bit more, the TLS evaluation. So specifically, we compare TASE to the most recent tool built for behavioral verification, which we refer to as CLIVER, short for Client Verifier. And the evaluation compares TASE and CLIVER side by side to measure how efficiently they perform behavioral verification of TLS network traffic against a known client implementation using OpenSSL. So both systems actually rejected a specially crafted network message designed to exploit Heartbleed. Instead, we're actually focusing here on the performance of the verifiers when they're run against a sample benign 3-minute Gmail browsing session. And I'll be talking about the lag introduced by implementing behavioral verification in line with network traffic. And the idea is that this lag definition is intended to intuitively represent the delay an end user would experience from the behavioral verifier. Okay, so on this slide, I've got some information from the paper comparing TASE and the previous work CLIVER's performance doing behavioral verification. The graph on the right should give you an idea of what lag looks like in the evaluation with TASE in black and CLIVER in gray. So in the graph on the right, messages are grouped into buckets depending on which 30-second interval they appeared in the trace. And within that 30-second interval, you've got a box and whisker plot of the lag times as well. So within each bin, the whisker plot will show you the first, second, and third quartiles, with the whiskers extended to, I think, 1.5 times the interquartile range. And the average is shown as a diamond, right? And so the numbers for lag across the board have decreased to the point now, following the initial evaluation from CLIVER a couple of years ago, have decreased to the point now where the most interesting lag occurs within the first 30 seconds of the traces, when the handshake occurs and also some of the most rapid transmission of the messages happens in the trace. And you can see that the worst case lag occurs for both TASE and CLIVER within the first 30 seconds. The worst case lag for TASE is 0.9 seconds and 4.2 seconds for CLIVER. All right, so to wrap up, I talked about our tool TASE that performs symbolic execution with the aid of transactional memory. Code for TASE is available on GitHub in the repo in the slides. It isn't tooled for fuzzing or bug finding purposes, but it's provided to help demonstrate performance in the benchmarks. And I also hope that the instrumentation that we created in the LLVM backend will be of aid to researchers looking to experiment with wrapping their own code in transactions, possibly for purposes outside of symbolic execution. Just given that the engineering effort to just embed transactions in code can be sometimes larger than expected. But yeah, I would be happy to answer any questions that you have. Thanks.